My name is Tim Zelazny. I'm with the Passive House Alliance Chicago. I'm the co-VP on the board, for those of you who I have not met before, but thank you for joining us today. I also work at ESD, which is an MEP engineering firm. And so engineers always want to know what's out there, latest and greatest, especially for passive house projects. And so who we have with us today is Mike from Swegon, and then Brett from Slipstream, representing the ComEd Energy Efficiency Program. And so Mike's going to be talking about HVAC, Brett's going to be talking about incentives for heat pumps. But before we dive into the presentation, which is AIA and PHI accredited for a CEU, is next month presentation, just coming out today, is going to be on solar hot water heating systems. And so keep an eye out for that. Other than that, please save your questions for the end of the presentation. Mike's going to start first, followed by Brett, and we'll do questions at the end of each presenter's presentation, just for the sake of time. Other than that, I don't think I'm missing anything. Mike, again, works at Swegon. He's going to be starting off the presentation. His bio is on the meetup page if you'd like to learn more about Mike, but what I thought was most interesting looking at Mike's bio is that he is a voting member of the ASHRAE Passive Building Design Standard, which I believe is a new committee as of last year. And so maybe we can pick Mike's brain on that towards the end of the presentation. But let's turn it over to Mike to present on HVAC for large buildings related to passive house. Thank you, Mike.
Thank you, Tim. Thank you for the invitation. I'm happy to be with you, even if only virtually today. And I will be happy to take questions of all those sorts, including about what ASHRAE is up to with passive building certification or standard writing anyway. A little bit about Swegon first. In the Chicago area, we are represented by Imbert, who actually had a role in getting our invitation to us today, so we appreciate that. I think we've got a representative from Imbert with us today. Hi, Kurt. Nice to meet you, actually, for the first time in person, or not. So a little bit more about Swegon. We are a global company at this point. We're not all around the world. We're kind of a medium-sized HVAC manufacturer. Started off in Sweden back in the 1950s. Today, we're active in 17 countries around the world, and we have, I believe we're actually at 16 factories now with a recent acquisition. We are and we have been very involved with passive house in Europe ever since PHI introduced the certification program for passive house ERVs, which is kind of the nature of what we're going to talk about today. So since then, we've found our product used on projects all over. You can go to the Passive House database and just search Swegon. You can find over 70 projects where our product has been used and found valuable for the project. You can also go to the FIAS database and do a similar search. It's just a little bit more difficult because of the way it searches to find where our product's been used, but that's something we can help you with. In addition to just ERVs, Swegon is really known as a ventilation manufacturer, and we have a variety of products that can be used in passive house projects, all projects really. So we've got, of course, the ERV, control dampers, diffusers, and transfer grills. So from a schematic viewpoint, we would use these dampers that I showed you, for instance, to make a constant volume system that would be a little bit more traditional, at least in my experience, in passive house projects in North America, into more of a variable volume project. That's something that is starting to catch on, actually, is that there is some extra energy savings to be had by using demand control topics or technologies on passive house projects. We'll talk a little bit more about that. So again, my name is Mike Woolsey. I am with Swegon. Our headquarters in North America are in Toronto, and I work out of my apartment in Minneapolis.
Hey, Mike,
Yes.
do we have anybody waiting in the lobby? I'm just double checking before
Yeah,
we.
I'm glad you did. We have 2.
Thank you.
Now we have 0. Morris and Milo. Okay. Very good. Welcome, new people to the presentation. Got them both. Okay. So we're going to talk about, you could say ERVs. That's the term that gets tossed around most of the time when we're talking about air handlers on passive house projects. But I'm going to talk about a kind of a broader topic, and specifically how these ERVs are actually applied. They're more like something else. They're more like an air handler with accessories than they are just ERVs most of the time. So we want to talk about that. We also want to talk about, what is it about passive house that makes a special kind of air handler necessary or desirable? And then get a little bit into some of the nuances, some of the different things that we do to integrate air handlers into these projects that we wouldn't otherwise do on a code building. So you can go to lots of websites out there with passive house content and find diagrams similar to this. I think there's pretty good agreement on what the key elements of a passive house project are. And we're going to talk mainly about the relationship between the air tightness and the continuous ventilation with heat recovery, because those are the two that kind of feed off each other the most. But also climate-specific insulation does have an impact on your HVAC system. Minimized thermal bridging also has an impact on your HVAC system, although it's more of an installation detail than it is anything else. And then high performance openings. So doors and windows and skylights and such are really the 5 characteristics of a passive house building. Without getting into the actual requirements, I think you've probably heard plenty of presentations about, we've got the PHI requirements, then there's the FIAS requirements. I think that much is probably pretty well understood. I'm assuming it is for this audience. So I'm going to skip right ahead to say that the passive house concept is widely accepted as working. It's not just a nice idea that gets down on paper and then that's the end of it. It's actually something that has been followed through. So I like to collect articles, and I've been collecting articles about how the energy savings actually is measurable, and over time it's been shown that in fact passive house buildings last. They stand the test of time and they save energy in a pretty predictable fashion. So you can read more about this in these references here. By the way, I'd be happy to share my presentation with anybody who's attending. Just let me know through your organization or directly.
Thank you.
So, is there a question? Nope. Okay. So airtight construction. It saves energy, but it requires continuous ventilation. And why is that? Well, first of all, let's look at that center picture. You can see a nice demonstration wall that was at a passive house exhibit a couple of years ago that shows what a passive house wall would look like, at least the guts of it. So we can see here the inside of the wall. You can see the furring strips here, followed by the airtight layer. Now that's something that you won't find on buildings that are just intended to meet code all the time, is that airtight layer. So the airtight layer is a really good thing. It saves a tremendous amount of energy on the passive house project. It improves comfort and cleanliness. Comfort because drafts are eliminated. Cleanliness because things like fine particles, even pests, can't come into the building through walls like they used to because it is so airtight. On the downside, there's the risk and the reality that when you have an airtight building, you are trapping moisture and trapping contaminants that you might not have been trapping before. Therefore, the passive house concept includes continuous ventilation with heat recovery to replace that moist and contaminated air with conditioned fresh air. So of course, there's more to the story. There we go. I put this table together to compare a code compliant building with a passive building. Don't really want to read it for you. So let's just hit the high points. And that is the infiltration. If we're talking about multifamily residential, and so far in North America, most passive house projects by square footage, and I think by any other measure, have been either single family residential or multifamily residential. Those projects are, if they're going to point at a code, it's probably going to be somehow related to ASHRAE 62.2 or something like it. In ASHRAE 62.2, you're allowed to take a pretty substantial credit for ventilation air that is delivered through leaks in the building. So the infiltration becomes part of the ventilation requirements calculation. So when you tighten up the building from an air tightness perspective, you reduce that, you minimize it. And the result of that is that you now need to get most of your ventilation air mechanically through some sort of an air handler. There's a real nice double benefit there. One is that now, in doing that, you've eliminated a huge amount of heating and cooling load from infiltration and moved most of the heating and cooling load to something that's in control, that is your ducted airstream. The actual analysis of that is really captured nicely in this document here, if you're into collecting articles like me. But it does describe how you shift from having sometimes as much as sometimes over half of the cooling and heating load is leaking in, or as a result of air leaking in through the building. So when you eliminate that, you're really then able to concentrate on that air coming from outside and heating it or cooling it adequately. And that turns out to be a much smaller energy requirement. So by comparison, if you put together an example building like I did here, you can run through some calculations to determine how much heating is due to infiltration on my project. If I'm going to build to ASHRAE 90.1, it might be up here. If I'm going to build to passive house, it's going to be down here. The percentages are just unbelievable, really. I didn't believe it when I first put together this slide, and I've looked at it a few times because I still didn't believe it. But this is the sort of numbers that people are dealing with when they put together a passive house project, is that you're just eliminating a huge amount of heating requirement because air is not leaking into your building. This is probably also why passive house seems to catch on more quickly and more abundantly in colder climates. Because of these values. If you don't really care, if you're in California and it's 72 degrees outside and it's January, you don't really care so much if you've got 72-degree air infiltrating your structure, because it's not costing you, there's not really much of an energy penalty when that happens. Okay, the next key characteristic is the insulation. Of course, we all know that good insulation helps you cut down your heating and cooling load. But well done insulation is a different story altogether. So here's an example of well done insulation. Again, it's that same demonstration wall at a passive house exhibit. This time we're looking at the outside. You can see how these slabs of mineral wool are nicely arranged inside the wall so that they're not ignoring this gap here. The thickness is adequate. The insulation's not compressed. And it's done right. And by doing that, the surface temperature has decreased. That's another thing that improves comfort quite a bit. Humans are very adept at sensing temperature differences from one side of their body to the other. So if and I've done this before, if I work in an office where my left arm is up against a cold dual pane window and my right arm is up against a warm building, that can be really uncomfortable to most humans. It can even trick the brain into thinking that it's drafty in the room. So it's a good thing, and it does help shrink the HVAC plant size, minimizes the heating and cooling load. Thus, it impacts the HVAC design. So there's other things we could talk about. We don't really need to talk about the Windows part here, even though we could. We're not going to, just for the sake of time. When we're talking about heat in the air, engineers are always looking at two types of heat. There's sensible heat and there's latent heat. Sensible heat really refers to what I would call thermostat heat, or just the heat that you sense with your body when it's dry out. So if I'm in Arizona, I'm going to get a lot of sensible heat. If I want to sample some latent heat, I'd go to Florida in August during hurricane season. That's the humidity component. It's also a form of heat. You can measure it. You can use different formulas to calculate how much of both types of heat you have to deal with on your project. This is background information because when you're on a passive house project, you really need to look at this maybe a little bit harder, especially in a multifamily project. You'll have to look at this a little bit harder than you would on a non-passive house project, because you tend to trap more moisture, thus have more latent heat to contend with year round. This slide is a bit of an apology because I toss around all of these different terms loosely. We're really talking about the same product when we talk about ERVs, DOAS units, makeup air units. I've looked at a lot of passive house projects in North America, and all of these have appeared when they're all describing exactly the same thing, and that is a continuous ventilation delivery device that is probably certified by the Passive House Institute or something like it. So what is an ERV? First of all, here's what it does. It takes outdoor air, it filters it, it blows it or sucks it through, in this case, a heat exchanger. And in this case, the heat exchanger is a rotary element. It's spinning around here up to 10 RPM, usually less. And as it spins around, it takes heat out of the air while only taking a small fraction of the air out of the return air. So the air flows from the outside, gets filtered, and then is blown downstream as supply air. And the air coming back from the building is also filtered, goes through the same heat exchanger, and is blown out. So in the summertime, outdoor air heats up this side of the wheel. As the wheel spins around, the air leaving the building takes that heat right back outside. In the wintertime, so in that case, it's a heat rejection. Sometimes that's called cooling recovery, which is fine. It just does describe what's happening, but my physics and engineering professors would cringe if I ever talked about cooling recovery, because it's really heat recovery working this direction. As far as the return air, I'm sorry, in the wintertime, the outdoor air is cold, so the hot air leaving the building heats up the wheel, and as it spins around into the cold outside air, outdoor air, the outdoor air heats up and goes downstream. So let me drill down a little bit further on that topic, give you some numbers to work with. I guess we're going to wait a couple of slides before we do that. This is a close-up view of a rotor that is a heat recovery heat exchanger. And you can see that it is layers of aluminum, a flat layer separated by corrugated layers or vice versa. So it's like a corrugated box, really. So these layers are spun up onto a hub, and air just travels straight through these chambers, tunnels, and aluminum is really good at absorbing heat and releasing heat. So on the hot side, the aluminum heats up. On the cold side, the aluminum cools off. There are other types of heat exchangers that you can use in this application, including plate exchangers, where instead of having a rotor that spins around, you have a physically bigger box full of these plates that are stacked on one another, so that the airflow, the cold air flows past the warm air, separated by aluminum, and heat flows from the hot side to the cold side that way. You can get approximately the same energy recovery rate out of a plate exchanger. The two downsides, one is that they do have a bigger footprint because it takes more space to have a non-moving heat exchanger, so your floor plan suffers. And the other one's not really a downside. It's just a recognition that sometimes plate exchangers are thought to have two properties that they don't really. One is that plate exchangers don't have any moving parts. Most plate exchangers, in order to prevent frosting or to provide good control, have moving dampers. So in this picture, you can see some dampers here. I mentioned that there was a second misconception, and that is that plate exchangers don't leak. You can actually, don't take my word for it, you can go look it up. Companies, certifying agencies that certify products like this publish data that show plenty of evidence that plate exchangers leak. Sometimes they leak more than, and by leak I mean cross-contaminate, more than even rotary exchangers. So these air handlers with energy recovery, or ERVs, come in all shapes and sizes. They can go in the roof, they can go on the floor, they can go in the wall, and the bigger ones, of course, go in mechanical rooms. So finally, here is the diagram I promised to show you, just giving you some sample numbers. I know Chicago can get colder than this, but just as an example, you can see when it's 15 degrees outside, heat recovery ventilator that's about 85% effective can deliver 65-degree air downstream without adding any mechanical heat. That is, there's no hot water coil, there's no electric heating, there's no direct expansion coil required. This number is actually pretty useful if it never gets colder than 15 degrees out where you live or where you're designing your project. Then 65-degree air might be adequate for heating in the wintertime, especially on larger projects and commercial projects, but not always. It's just meant to give you an example of what a heat exchanger can do for your project. The idea, though, is that most of the time it's going to be above 15 degrees. Therefore, the supply air temperature will also most of the time be greater than 65. So that if you do have supplemental post-heating, post-cooling, then that is only used a small number of hours per year on a passive house project, especially. So this first slide was for a heat recovery ventilator that is designed only to change the temperature of the air, the dry heat. It's not doing anything about the latent heat or the humidity. So this slide is for that other type of ERV, the type that is capable of transferring both types of heat. So hot goes from hot airstream to cold airstream, and moisture goes from wet airstream to dry airstream. So in the winter, like we're showing here, when it's really dry outside, if you're not used to looking at grains as a measure of moisture, let me just say that 12 grains is really dry. We would expect in a building to be somewhere in the 65, maybe 60 to 65 grains per pound region. It's an absolute measure of the weight of the moisture in the air. So in this case, really dry. And this dry air is picking up moisture through the heat exchanger and delivering it to the supply air side. So that in this wintertime situation, a building that's still pretty dry, it's not being dried out terribly because of the heat exchanger. In fact, the heat exchanger is helping keep the moisture level up, which is usually desirable in the wintertime. Okay, now let's talk about certified air handling units with heat recovery. And I'm talking about those types that are used on passive house projects. Passive house air handler certification has some goals. It's not meant to just be another way of certifying your heat exchanger or your air handler. It's meant to offer something more. For instance, we're actually trying to achieve maximum thermal energy recovery, and we're actually trying to exceed a given minimum. At the same time, we're trying to maximize our energy recovery while minimizing the electrical consumption. So that's an interesting trade-off. That's one that's extremely valuable on passive house projects, but often overlooked. Another one of the goals of certification is that data is made readily available to designers so that they can populate fields in their energy modeling software easily and quickly and accurately. And that is as opposed to the other third-party certification providers that really are just certifying that the data given to you by a manufacturer is accurate and reliable. So let's look at the Passive House Institute certification criteria. And let me just take a sidebar here that FIAS has a pilot program for certifying energy recovery ventilators, but because it's a pilot, yeah, I can't really talk too much about it because so far there aren't any participants or that have been certified. And we're talking about the large units as well. So I'll talk about existing programs for certification, knowing that every single one of the hundreds of projects we've looked at in North America have used either AHRI certification or PHI certification. So first, PHI certification. You can go to the PHI website. You can download these certificates from any manufacturer that's certified and get information on what was it that the manufacturer did to gain certification. And in this case, it's shown right up front that, okay, this manufacturer got their certification, like all the others, because they achieved a minimum heat recovery rate of 75%. They did not exceed the minimum specific power or specific electric power requirement of 0.45 watt hours per cubic meter. That's 0.765 watts per CFM. Leakage did not exceed 3%, and that is both internal and external. So that's casing leakage. That's also cross-contamination and some other things related to comfort. The idea here is that there are actually thresholds that have to be met in order to get Passive House Institute certification. By comparison, AHRI has a program called AHRI 1060. It's a very robust program. It's very much the same sort of a program that Passive House Institute has, except for one thing, and that is AHRI 1060 doesn't have any minimum requirements. If you have an air handler that you claim has a sensible effectiveness of 32%, and AHRI can duplicate that in their lab, then you can become certified. PHI, of course, I just showed you that they have minimums. So that's the big difference, is that AHRI 1060 is going to verify that the data that manufacturers provide to their customers, whether through brochures that are printed or through online selection software, that data is accurate and reliable. There's a bit of a difference too in the way things are calculated. You can actually have a different heat recovery effectiveness calculated by PHI than you would by AHRI. And the reason is shown here. AHRI does two things that are different. One is that it allows for you to adjust your values, your heat recovery values, based on the amount of airflow given. So you can actually kind of, you might say, play with the numbers, or just say that, well, in the way that I like to apply my product, it's always going to be with this different offset. Passive House Institute doesn't allow you to do that. The other difference is that the Passive House Institute certification has this waste heat term, and that is you have to include the heat that is delivered to the airstream by the fans, which is a useful thing to know, because you do get degrees of temperature rise because of a fan, and that is included PHI but not an AHRI. So it's good to know, and it's good to consider that it would be reasonable to expect that depending on the application, a manufacturer's product might be certified by both organizations, and the data can actually, the heat recovery rate that's certified by either organization is actually different at the same operating point. Seems counterintuitive, but it has to do with the math. When we talk about the electrical power, we're not just talking about the fan power, we're talking about both fans. So we've got two fans in a heat recovery ventilator. We also have another motor that spins the heat recovery device. If you're using a plate exchanger, you actually have the benefit that you're not consuming energy turning this wheel. It's a very small amount of energy, but you do have energy expended moving those dampers around. You also have energy used for the controller. And all of that is added up, measured at the same time that the heat recovery effectiveness is being measured. So you know that at the rating point, you have a certain specific power consumption. There's also an application difference. If you're going to do a code compliant building, typically what gets applied is an air handler that is the smallest size needed to get the job done. And by that, I mean, if an engineer were to come to a manufacturer and say, can you help me? I need a 3,450 CFM air handler. What do you have to offer me? In this example, this manufacturer would offer a size 20. It's the smallest unit that will get the job done. Well, why do we pick the smallest unit? Well, for decades, the idea has been that, well, we're doing our job in not selling a unit that's too large. Therefore, we're keeping the first costs down. Therefore, the end user benefits. While that may be true for the end user, or sorry, the first cost, the end user may actually pay an ongoing penalty year after year in excess energy consumed. So when we apply a passive house air handler, it might be the same brand, might be the same device, except we typically find ourselves going with a larger unit. And that larger unit is responsible for quite a bit of energy savings. So in this example, it is the same manufacturer, same airflow. The lowest first cost air handler requires about 66% more electricity to move a CFM of air than does the PHI certified unit. Mainly because instead of using electricity to force air out of the device, we're using electricity not to get air out of the device, but to blow it downstream. The ratio changes. So we save a lot of energy that way. So the takeaway there is that on a passive house project, especially the larger ones, you can expect to have maybe you might even call it an oversized unit, or at least a unit that's a little bit bigger than it otherwise would be. Another requirement that Passive House Institute has that AHRI doesn't is that the supply air temperature can't really ever go below 62 degrees. That's really a comfort thing. So what they're saying is that, okay, even though you say you have, in this case, 84% heat recovery rate, we don't want that to take place only when it's 0 degrees outside and the discharge temperature is 51. That's not what Passive House is trying to accomplish. So throughout, and the more I do this, the more I'm impressed with the way that Passive House Institute is able to influence both energy use and comfort by their program requirements on the certification of air handlers. Leakage comes in two forms. Passive House Institute certifies both. The requirement is that you can't exceed 3%. So one form is casing leakage. We don't want to have a casing on our air handler that leaks for a couple of reasons. One is a passive house project is intended to be airtight. If you have a really leaky air handler, that alone could prevent your passive house from being airtight. Another reason is that you don't want the air handler to either suck air in from the mechanical room or maybe the rooftop, or blow it into the mechanical room or the rooftop because it leaks. That would just be energy used for no good purpose. The other reason, it's a big reason, especially right now with COVID, is cross-contamination. How much air flowing out of the building gets back into the supply air. Passive House Institute allows no more than 3%, which is a pretty low number, actually. You can see from this diagram that we're filtering the air. You can get a variety of filter qualities. We always have MERV 13 on the outside air, but with COVID, it's a good idea to also use MERV 13 in the return air to trap any contaminants in the building already, so that this very small amount of cross-contamination is clean air, just as clean as the outside air. The certificate also tells you over what range this particular manufacturer has product that's passive house certified. So it's not an entire product range that is automatically included. In this case, this manufacturer is capable of delivering about 3 times or 4 times, maybe even 5 and 6 times this amount of airflow through larger air handlers, but those air handlers don't meet the minimum requirements of passive house. Therefore, the manufacturer is limited. And the way the manufacturer is limited is that because passive house is all about energy savings, and passive house promotes low pressure duct design, manufacturers are not allowed to test a product above 1.5 inches, sometimes only 0.9 inches, depending on the size of the unit. And that's another way that Passive House Institute really influences the design of buildings by saying, we want you to use a Passive House certified air handler. To do that, you're going to have to keep the external static pressure down. The end result being that that manufacturer has a limited range of products that apply to your product. Passive House also, PHI, I should say, also certifies that the ERV has onboard controls that are self-balancing, so that within the supply air is always within 10% of the return air. There's 2 situations. One can be negative pressurization, either because the building isn't balanced, or maybe a bunch of people open their windows, or maybe just it's a really windy day there in Chicago. And the way it is, that wind pressure is causing air to enter the building. Even an airtight building, a relatively airtight building, can receive some air from the outside that would cause the building to go out of balance. The way you keep it in balance, no matter what the conditions are, is to have this sort of control mechanism built in. And of course, the opposite is true too. You could go negative or positive and have your ERV managing the difference. Okay, so the next topic then is integrating these ERVs into your Passive House project. Is it really worth it? Do you get much benefit? The answer is yes. You can compare here a full analysis that was done for a building, in one case using a code compliant air handler, and in case number 2 using a Passive House certified air handler. And the end result was shows that the bottom line is about 10% less energy than its competing code compliant air handler. Most of that is coming from less fan energy, which is really interesting because that's the whole idea. We want to use less fan energy because it's such a huge component of the building's overall energy consumption. And so you can see from this example that it actually pans out that way. I won't skip over that you might actually end up using a little bit more for heating, which seems counterintuitive. And the reason for that is because in this example, we ran the model using free cooling, and passive house free cooling is available at lower temperatures than your typical building, maybe down to 45 degrees. But to use 45-degree outside air to cool your building would require a little bit of reheat through some mechanism, maybe a heat pipe. Every building's different. I can't guarantee you that these numbers would be true for your project, but I think the message is that you can actually look at numbers like this just to see what the differences are. When you're specifying ERVs for passive house, it pays to step back a moment and just realize that passive house does not speak to product safety. So you can't just drop everything else that you've been specifying on your projects and use the passive house certified passive house certification in lieu of things like UL 1995, which is kind of the umbrella standard for air handler safety. So you'd want to make sure to have a look at that. Some other requirements too. The main one is safety, not part of passive house certification. Flow rates. Well, flow rates are going to be either up to your local code requirement, or maybe your local code just defaults to 62, ASHRAE 62, 1 or 2, or passive house. You really need to compare them and figure out which one is the most rigid and use it. Most cases I'm aware of, local code dominated. I talked before about low pressure duct systems are very important in passive house and influenced by the certification process. So target velocities depends on which document you look at. ASHRAE allows some pretty high duct velocities in typical buildings if you look at their documents. But if you're limiting yourself to passive house requirements, you'd want to be in the 400 to 600 foot per minute range. What that means is you have to consider either larger ducts or shorter duct runs. And when you're designing your ducts or your air distribution system, there's a growing trend that we see in North America, even in Europe now, the duct sealing is a huge component. And a colleague of mine shared these pictures with me recently. From thermal imaging, you can see what difference duct sealing makes. So in this case, we've got this ceiling here has 2 round diffusers in it. This diffuser, this one, does not leak at all. The thermal imaging is showing not the discharge air temperature, it's showing what's going on behind the ceiling. So in this case, we can see that this diffuser, for whatever reason, is not sealed up well, and that there's cold air leaking out all over the place above the ceiling, which is very common in buildings. So duct sealing of less than 3%, we're starting to see specified. I know Passive House Institute also recommends a 3% number. So ducts, therefore, on a passive house project would need to be tested, certified, but first of all, specified to some SMACNA standard. Occupancy control is only starting to be used in North America on passive house projects. The first couple hundred or so multifamily projects have been using constant volume airflow. Lots of energy being saved on those projects, but it's shown and can be shown pretty easily that if you add demand control ventilation, you can save even more energy. By adding the same devices, these dampers here for decreasing the flow, these dampers can also be used to increase the flow to provide more occupant comfort. So by demand control, we're really talking about turning down the amount of air distributed through the building when the building has lower occupancy rates. So let's say you're in an office and you go home for the evening, or you're at home and you leave for the office in the morning. You're leaving behind an empty space that doesn't really need any ventilation. So you can turn down the ventilation so that these fans don't have to work so hard, so that they can save some energy. Related to that, on the duct design side, you have choices when you're selecting how you're going to do air handling. You can go completely centralized, or you can go completely decentralized, or you can do something in between. So by that, I mean centralized means you have one air handler for the entire building. And since I'm focused on large buildings for this presentation, this example is for a large building. And we're showing a big air handler, one big air handler in the basement. And this yellow line represents the longest duct run. So it takes fan pressure, external static pressure, to get that air all the way down to that last diffuser in the furthest away space. Decentralization involves making the duct runs shorter. In this case, I'm showing a partially decentralized system where we have one air handler per floor, resulting in a dramatically smaller duct run, shorter duct run. A completely decentralized unit would be similar to the picture I showed earlier, where you have one ERV per apartment. In some cases, you might have one ERV per room in the apartment. That would be totally decentralized. I could probably talk for an hour just on the differences between the two. I think the most important that I hear customers talking about is decentralization involves adding air handlers at the expense of complicating the air tightness testing and complicating the maintenance. So when you are doing an air tightness test, you have to seal up your air handler outside air. And if you've got 100 apartments and each one has an ERV, that means you have 200 duct inlets and outlets, 100 of each, that need to be sealed up for both air tightness tests. And then on the maintenance side, it's been shown that especially perimeter mounted ERVs are difficult to get to for maintenance. If you need to clean the screen on the outside intermittently throughout the year because you've got, say, cottonwood on the filter on the outside, it's sometimes seen and been shown that the only way to really get to that is for the maintenance guy to lean out the window and try to service it that way, or get a lift, depending on how tall the building is. So there's a lot of comparisons there. There's no right answer. There's no perfect answer. These are just some of the situations that I'm aware of. So these two slides kind of show you what I mean. We have a single air handler on the roof serving 3 floors, no more zones than that. Well, this air handler only has 2 points that need to be sealed up for air tightness testing. If you go to 2 air handlers, then you now have 4, and so on and so forth. So that just by going to 6 ERVs, you've now gone to 12. 12 is not a bad number. It's when you get into the hundreds that you really start to have lots of extra labor hours involved with your air tightness testing and maintenance. Low pressure duct systems can also be implemented through things like cascading airflow, where you deliver air to the living zones or the occupied zones and let that air transfer into corridors or kitchens and toilets or closets, for instance. So in this case, it's shown that the air is moving from this office into the corridor through a transfer grill. In this case, the transfer grill is light proof and soundproof, which adds privacy when compared to just letting the air travel under a door. To allow air to travel under a door, you have to leave a gap that's big enough to let light through, and often impossible to maintain privacy. So this is, as you can see, instead of having a return duct go all the way over to this perimeter space, we only needed to have it very close to the trunk, close to the return air grill, because the air has transferred itself under pressure without ducts. Still on the topic of integration, and we're wrapping it up now. Indoor installation, there's not really any thermal bridging risk because the air handler is kept at the same temperature as the mechanical room. The outside and the exhaust air ducts would still need to be insulated, but we're giving up valuable floor area. So but it's still doable. And we do see it on passive house projects. We also see ERV outdoors on passive house projects in cold climates. So in this case, here's a project I got to visit that was under construction, and you can see that they put some thermal isolation blocks here because their thermal bridge modeling indicated that this equipment stand was just transmitting too much energy between the building and the outdoor environment. So, for instance, there would be a condensation risk below this that could result in rust. It could actually result in damage to the building. So those are the sorts of things we see get special attention on passive house projects. And also there's no floor area given up when you take this approach. You just have to insulate different ducts. Cooling. Again, this is one of those topics I could and would, well, I'm not going to spend an hour talking about. I'll just say briefly that passive house does have the ability to take advantage of extra cooling hours. Most projects have a balance point in the 50s, mid 50s. And by that, I mean that anytime that a reasonably sized commercial building or even multifamily building, anytime the temperature is above 55 degrees outside, it's probably warm enough that you need to provide cooling to parts of that building. Passive house, because of the nature of passive house, often can get away with or actually has a requirement of cooling in a similar application when the temperatures are in the 40s. The good news is that's happening while it's in the 40s outside. So you have all this cool air at your disposal, and you want to be able to have your ERV have controls that can take advantage of that free cooling. I mentioned before that post-heating and post-cooling, certainly part of the passive house concept. Many ways of doing it. There's a lot of interest in going all electric right now. The idea has been that all electric always means VRF, but there are some interesting substitutes for that. Heat recovery chillers are a possibility. District heating and cooling is a possibility. And I'm sure there will be some interesting concepts in the future as well. But the idea is that, yes, you are allowed to add heat at the ERV. You can even add it outdoors, so you don't always need to. Some manufacturers will require you to do that. Just if you do that, just remember to include this preheat coil in your energy model. But also consider that often, I don't know what the percentage is, but the ERV will be a pure ERV delivering air downstream into the back end of a fan coil unit where it's then tempered to the occupant's liking. So there's an integration where we're showing, okay, this is more than just an ERV. It's an ERV with filters, preheat, post-heat, and post-cooling. So again, the idea is that this ends up being a relatively small condensing unit where the first stage of heating and cooling is the energy recovery device, which satisfies the temperature demands most of the time. And with those few days or hours a year when it's too hot or too cool outside to be comfortable indoors, with that heat exchanger working really hard, then a signal is sent to turn on the condensing unit to add heating or cooling. Skip that slide. So last couple of slides here. Here is what, the previous slide was kind of diagrammatic. Here's what an actual ERV can look like when it's fully outfitted for a passive house project. So this is a dormitory at Wheaton College in Massachusetts. This one ended up being the first passive house dormitory in North America. And it's got 2 ERVs in this configuration here. We're only looking at this one. So this is ERU3 here. ERU2 is behind here. So we've got the control dampers, the exhaust hoods. Let's see, we've also got cooling coils and heating coils. And then the air is ducted down into a shared shaft. Actually, they're not shared, they're almost shared, but they are using a shared condensing unit, kind of a hallmark of a VRF system. On the idea of comfort, I didn't really talk too much about it, but the pass-pass concept really is largely about comfort. And that does require some slightly different thinking than what we would do on a code compliant building. Sometimes we know that ASHRAE 55 is specified on a project, but even ASHRAE 55 doesn't quite align itself perfectly with passive house. So that means that when you're selecting your air handler, you have to consider that you need to take a good look at the psych chart and make sure that you're in the comfort range of ASHRAE 55 to be sure, but don't get into this area up here, which is actually more relative humidity than we want to have in a passive house project, or any project for that matter. It's comfortable, yes. It's safe for the building, no. You really risk condensation if you're up in this triangle here. And even though you can be comfortable in these conditions here, you might not be healthy. So by that, I mean that below about 40% relative humidity, there's ample evidence that yes, it's thermally comfortable, but you may pay the price in dry skin, dry nose, but also an increased likelihood that you'll contract something out of the air. So we want to keep our designs, summer, winter, or shoulder season, in this narrow band of comfort. And it has a lot to do with how you select your air handler. You want it to be capable in all those scenarios. So what are the benefits of applying a passive house certified component, in this case an ERV? Mainly, you want to reduce energy consumption, but you're going to get third-party verification that you're going to get what you were expecting. You're going to simplify your modeling process because you're getting data from the manufacturer that you can just copy right into the model. I should add there that Passive House Institute, if you select a PHI certified ERV, the data is already in the model. You just need to select it. And then there's the cost. You don't want to have unpredictable testing of your ERV out at the job site in January. That might be required if you use a non-certified unit. Or even during the design phase, you don't want to end up taking a penalty on the heat recovery effectiveness because the unit isn't certified. So those are the reasons that you would want to consider at least using a certified ERV on your passive house project. So that's the end of the course. Some other things I can offer to you if you're interested, just stay in touch about it, is questions to ask about your passive house. It's a document we've put together that kind of lets you build from the experience of others. And then there's a brief summary, a one-page summary of this presentation as well that's printed. So that's the end of it. I'd be happy to take questions or turn it back over to you all in Chicago.
Thank you, Mike. We're going to jump over to Brett's quick presentation on incentives for the residential market. But in case somebody has to drop off, Mike, what's the best way to get the CEUs for this course?
The best way is to contact me, I think. I don't see a fearful number. There's 24 of you online, so I think you can just contact me direct. If you want to gather up the names yourself, that's fine, but I'm happy to just take the inquiries as they come in, and then I'll send a certificate. If you include your AIA number, I'll just put that in myself.
Okay. Yeah, I would recommend everybody reach out to Mike directly with your AIA number for the CEUs. Mohammed, I do see you have a question, but we're going to turn it over to Brett really quickly to present on incentives on the ComEd Energy Efficiency Program. And before I turn it over, just a reminder, there is an incentive out there for these larger scale passive house projects in Illinois through the Illinois Clean Energy Foundation, up to $2 million. And so I'm going to turn it over to Brett to talk about residential incentives.
All right, thank you. And I will be pretty quick here. Just got a few slides I can share. Yeah, you mentioned the up to $2 million incentive through the ICECF, which is great for larger passive house projects. There are also utility energy efficiency savings here. And if you haven't heard sort of a pitch before, the whole reason these programs exist is because they're funded by utility ratepayers. And so if you look at your energy bills, there's actually a little line item in there where we all pay into these energy efficiency programs. And so we always say, we encourage people to, you're contributing, you should take advantage of the programs and the services and the incentives to get the benefits. And these programs are mandated by the state, and the utilities implement them to help the customers save energy on their bills. So across ComEd's portfolio, there are all kinds of different offerings for different applications. On the commercial side, everything from technical assistance for different applications, including new construction there, rebates and incentives for different applications, discounts on products, and then optimization services. Similarly, on the residential side, energy assessments, rebates on everything from light bulbs when you go to the store to HVAC. There are incentives out there for high performance heat pumps if you're looking at individual pieces of equipment, and contractors in the area are generally set up to handle those individual equipment rebates. And then there's a whole portfolio of programs specifically for income eligible, including an affordable housing new construction program, which some folks on the call here may have participated in previously. There's some pretty hefty incentives, and passive house projects have participated in that. Passive house projects would typically meet the requirements for that program. And in that case, the incentives are north of $4 a square foot for official affordable housing. What I quickly wanted to introduce here is a brand new pilot program that was launched in 2020, specific for high performance, all electric new construction of single family up to 4 flats. So it's more the residential scale. We're offering $2,000 per home for incorporating a set of sort of best practice energy efficiency measures. In the case of multiple unit, if it were up to a 4-unit building, that would be $8,000 incentive. That's how it scales by unit. The requirements, we're talking about all electric, so heat pump, space and water heating, and clothes drying as well. Requirements for a tight envelope, which we lay out in our program literature. A passive house project would blow those away. High efficiency heat pump equipment, heat pump water heaters, Energy Star appliances, efficient plumbing fixtures, LED lighting, pretty standard, and then smart thermostats if you've got a system that works well with those. And so I've got a link here at the end of the presentation where you can go and find out the details of this program. It's not specifically a passive house program. I would love to say we're making a jump to a big offering specific to passive house, but a passive house is 99% sure it would qualify for this program, assuming that it is going with all electric space and water heating. And of course, probably preaching to the choir here, but the really exciting thing about a high performance electric home is that you have that opportunity to offset your energy consumption with renewable energy. ComEd does have some resources up there if you're interested in learning more about solar applications and rebates from the state and federal level. There's resources on ComEd's website. This year, like I said, it was the first year of a pilot. We had about a dozen participants, and it was a broad range of participants, custom single family, spec single family, accessory dwelling units. So we got some coach houses, some townhomes. We've got a 3-flat project, a couple of 2 flats. It's a really good mix of project types that have participated, and we're trying to build up these case studies and take this thing on a roadshow and convince more builders to do it. I love working with some of the leaders in the industry that are probably on the call here today. contact me if you feel like if you would qualify, or if you've got a project that could benefit from, the sort of ComEd marketing and of course the incentive. By all means, contact me. And we're pursuant to the purpose of these programs, we're trying to scale this and help more customers attain this. And so likewise, if you have suggestions of friends or colleagues or competitors who are greenwashing, let me know, and let's get the word out about this program and try to move the market. I think I'll skip the part about why you should do this. I think this passive house crowd probably understands the quality and the comfort and minimizing HVAC sizes and all that. And we're starting to see uptake from or interest from corners of the market that maybe wouldn't have gone all electric in the past. And so,
Hey, Brett.
Yep.
How's it going? Good to see you.
Good. Who we got there?
This is Tony.
Oh, hey, Tony.
So I saw you. I didn't see cooking on there, so you could still have a gas range and still qualify.
Yeah, you could. Oddly enough, we didn't include that in the requirements this year because from an energy efficiency standpoint, it doesn't really make a huge difference. Everybody that participated this year went with induction cooking, so I think it's kind of a moot point. But if you got somebody that's really hung up on that gas range, it's not going to be a barrier for this program anyway. But
I have witnessed that. It's a thing here in the Midwest. And then, so am I understanding right, the application process begins with you, starts with you?
Yeah, that's right. So here's the website, comed.com/electric homes. There's a pre-application that is on there that starts the process, or you can just contact me and let's get talking. At this point, it's a pretty personal process. So contact me and let's go. It's pilot. But the details of the program are up on there. Also, on November 5th and November 12th, we're hosting a couple of roundtable discussions with a couple builders who participated this year who are willing to sit in and talk and share their experiences with some prospective participants. And the idea is, what we're hoping to do with this program is get the stories from the people who are starting to do this stuff and share them. And the great thing about this community is that most everybody wants to share their experience and share the technical challenges and how they overcame them. And I think that's the path to building some momentum around this. So if you're interested in joining one of these roundtables, shoot me a message. I think that's the end.
Thanks, Brett. Now we'll dive into questions, and if you could type your question into the chat function, just so we know who is asking the question. And but before we do that, thank you, Mike and Brett, for very thorough but succinct presentations. I was scrambling trying to think of questions because you were asking them or answering them as we went. But the first question we have is from Mohammed. And to summarize, Mike, it's in regards to the rooftop installation. And so is there a climate in the US where you wouldn't recommend installing the ERV on the roof, either due to temperature, humidity, or is that really not an issue with the Swegon certified units because of the insulation and minimum leakage you have?
Yeah, there's two angles to that question. Is the rooftop part is probably the easier part. Manufacturers either do or don't have a rooftop suitable unit with things like roof and extra insulation, water tightness, things like that. As far as the ERV versus HRV part, if you get out west and sometimes a little bit southwest, there's really no added benefit in having the enthalpy recovery or the latent heat recovery. You can get away, you'll save 99% of your energy by just transferring the sensible heat. And you can do that either indoors or outdoors on the roof, or outdoors on a pad for that matter.
Thank you. Mohammed, let us know if that did not answer your question. But moving on to
Can I ask in this way? Yeah. Hello, Mr. Mike.
Hello.
Yeah, this is Sami. I'm a grad student at UIC, and I'm also an HVAC engineer. And after going to the presentation, I just have one doubt. The reason I've said about outside limitation on outside air temperature is, let's say we have a temperature, we are designing a passive house in Florida, which has high dry bulb and wet bulb temperature and high humidity range and that. So since we don't have a mechanical dehumidification there, can the wheel itself is efficient to remove the remove the sensible and latent load, since enthalpy removes sensible and latent load from the air? Is it like capable of providing thermal comfort within the building?
No, I would say that this sort of heat recovery device, energy recovery device is not capable all by itself. There are manufacturers that specialize in dehumidification. Even those manufacturers would do what we do, and that is use some sort of post-cooling coil to take the temperature down, get the dew point down, to wring the moisture out, and then because use that dry air.
Yeah, because the only other option, because I worked in Dubai, wherein we used to have much DOS applications. So the only other option other than that is providing a heat pipe, probably like pre-cooling without without cooling coil.
Yeah, and even a heat pipe may not get you there, especially in Florida, since that's your example. In other climates, maybe, but for instance, Chicago might have a shot at it. Actually, I've never really looked at numbers for Chicago specifically to use without, and maybe Tom, my colleague, could chime in on that, what his experience is with the numbers on Chicago projects, or Kurt, if you have any specific experience there.
Yeah, that's it. Thank you very much for the answer.
Thank you.
Hey, Mike,
Brett.
I got a couple questions, if I may jump in. This is Tony Hollub.
Hey, Tony.
In terms of so you mentioned the recovery rates are, well, I guess maybe I'll just ask the question this way. For passive house projects, residential projects, we often aim for, we'll say 85% effective recovery, heat recovery. What are you seeing for, because you guys also do larger commercial projects as well as multifamily projects. What do you see for just the commercial projects for your equipment versus those multifamily projects? Are you
really in the same ballpark, in the mid to, I'd say low to mid 80s is typical, and very high 70s, like 78% on the total or the latent recovery.
Okay.
All depends on the climate. Sometimes it's exactly the same. 85% both heating and cooling, and 85% both latent and so there's really 4 measures: summer, winter, and latent sensible. But mid 80s is a good working number.
And code requires around 50%.
Yeah.
And then I guess kind of a follow-up question to that. So you're primarily, or I don't know if I want to say it this way, but you're best known for being a European manufacturer and are moving into the North American market, have moved into the North American market. Of the projects here in North America, kind of what's the split of passive house projects versus just commercial projects, efficient projects? How would, and do you work on just sort of built to code projects, or do you guys really specialize in the higher end projects?
We have kind of a split between the high end passive house projects or the passive house like projects, and that same subset would be the kind of the sustainability, so the net zero targeted buildings. And then we also do a fair amount of work in buildings that are really intent on using VRF integration. which sometimes that actually goes into the Passive House project, but we seem to be getting our niche, if you want to call it that, in the high performance buildings.
Thank you.
Thank you.
Any other questions for Brett or Mike? Brett, do you want to circle back on your involvement with ASHRAE and Passive House buildings? If I said Brett, I mean Mike.
All right. If you're involved, Brett, you can go ahead.
No, I was going to kind of scramble to make something up, so I'm glad you're involved.
Yeah, so Tim, you're right. ASHRAE set up Standards Project Committee 227P, which is the passive buildings standard. It was actually authorized almost 2 years ago at the ASHRAE winter meeting 2 years ago, what will be 2 years ago in January. The first meeting then was in Kansas City last year. And since then, the committee's been working diligently, but these things are slow. The committee's actually, I'm on that committee, as you said, and I can tell you that the committee's actually now finally putting words on paper that will someday become a proposed standard. And the idea is that there's categories, things that will be addressed include loads, air tightness, all sorts of supporting things like ventilation is one of them. As you might expect, I'm involved with that part of it and some others as well. So there's about 25 or 30 people that are active, and we meet regularly. So the next thing that you can expect as a community is that, first of all, you can monitor progress a little bit just by the ASHRAE website. But once the proposed standard gets to a place that the committee believes is ready for public review, we'll vote. And if the entire committee agrees, yeah, let's send this out for public review. Literally anybody that finds the public review form can read it and make comments, which is actually one of the more valuable parts of standards development. So we had hoped to have that first public review early next year. Remains to be seen if we'll hit that target or not.
When it comes to a vote, is it ASHRAE only members or that have a vote, or is it public?
The vote is ASHRAE committee members only. So even the general ASHRAE member cannot vote on the standard, but the voting members that are appointed by ASHRAE to be on the committee are the ones that vote on it. But I think most people don't realize that the public comment period is pretty rigorous. If a comment or if a question is asked, the committee must respond. So that's why I say it's a very valuable part of the process and very insightful too, because sometimes, often my experience, I've been on other such standards writing committees, and you do actually get some really good insight by going to the public like that. And then those comments and the responses all become part of the public record.
Thank you. And is the intention of the standard to be more of a stretch code or a standard that gets adopted fully by ASHRAE into future 90.1?
It is intended to be, I guess, more of a stretch code, even though we're not calling it that. So it will not be, at least it's not intended to go into 90.1. It's intended to be a standalone. Simultaneously, ASHRAE's, interestingly, I think, working on a net zero building standard. So it's as a specifier, you're going to kind of have this menu of what type of building do I want to design? Do I want it to be a 90.1 building, a passive building, or a net zero building? You can pick from your standard. So part of the process I get to go through is, for instance, on ventilation, I can look up 90.1 and look for conflicts. Like passive house is just like 90.1, except in these cases. And we don't want to say that this is okay in passive house when it's not.
Thank you. Any other questions for Brett or Mike? Well, thank you to the presenters again. Great presentation. It's been recorded. We'll be sharing it on the Passive House Chicago YouTube channel in the next week. And just a reminder, next month's presentation will be on solar hot water systems. And,
All electric hot water systems.
oh, thank you. And with that, have a good night.
Thanks, everybody. Good to see you.
Thank you.
Thanks, everybody.